Hello, good evening. All right, so welcome. So for today's class, as I sent in the announcement just now, we will first start off by going through tutorial 4, okay, where we're going to cover some concepts on the interrupts, multi-threaded programming, and the semaphores and mutex that we have studied so far. Okay, after that, then we will go on to finish up, okay, the rest of the multi-threading lecture, okay, and towards the end of that, we are going to go through some demo code, okay, on the using a message queue and task queue. All right, and you need to sort of know how to do that so that you can complete the assignment 2. All right, so assignment 2 is based on the OS. All right, and you need to develop the code for the application. All right, and the task queue or message queue are basically the ways in which you need to approach that. Okay, so the later part when we go through the demo, okay, so you have a better idea how it works and how you can integrate that in your assignment 2. Okay, so let's get started with the tutorial. Okay, so I also been receiving some queries about the term paper, so later I'll also discuss a bit about that. Okay, so that all the common questions that people will be asking, I will try to address them so that it is clear. Okay, so let's go through tutorial 4 first. Okay, so tutorial 4 is based on the things that we have covered in the second half. Okay, that means after the MIPS. Okay, so in this first question here, basically, what we are doing is we are asking, or we're giving a flow chart of ISR. Okay, so ISR is basically the interrupt service routine. Okay, that handles the input device and processing the input data and sending it to some output device. Okay, so you can think of it as any application. For example, you have data coming in through the Wi-Fi or network port or something. Okay, and then you process that. So whenever data comes in, you have an interrupt to process the data, and you try to send it somewhere else, correct? So maybe after you finish, maybe you try to save it to the disk. So this output device could be a disk drive, okay, and you want to save it to the disk drive. Okay, so you need to wait for this drive to be available, and then you write to it, and then you can return. Okay, let me see, end the interrupt. Okay, so every new data packet that comes in, you do some processing, okay, in the interrupt service routine, write to the disk drive, and then you carry on. All right, so this is basically how your ISR is written. Okay, and the question is asking us to look at potential issues with this design. Okay, how it can be improved within the context of a single threaded. Okay, so in this example, we are still looking at it from a single threaded perspective. Okay, single threaded means we haven't go into multitasking. Correct? It's still a single sort of super loop. Okay, the only additional thing you have is this concept of interrupts. Okay, that means you can handle asynchronous events that need immediate attention. So that is the question here. So let's look at the first part A. Okay, what are the potential issues with this design? Does anybody have any idea or to share? You can put in the chat if you want. Okay, does anybody see any or see what is the potential issue with this current design? Okay. Okay, so nothing on the chat yet. Okay, so maybe you're still thinking about it. All right, so if you look at this, the issue here, okay, the main issue is this part over here. All right, why is this an issue? Because, okay, firstly, let's come back to the idea of what is an interrupt service routine. An interrupt service routine is supposed to be a very short piece of code that captures the event, okay, an event, and you want to process it as quickly as possible. Okay, that means you want to capture that data or that trigger the moment it happens. Okay. Now, when you have an interrupt service routine, one of the most important things about it is that you want to keep it very short, okay, and direct. That means you want to only do what is really important in the interrupt service routine. And after that, you want to be able to carry on with the loop. Okay, because you have to remember that this ISR is separate from the loop. So you have your main while one loop. Okay, if your main while one loop is running, okay, you're running and then you go back and you carry on. Okay, this is anytime can happen. Okay, you need to break away from the loop, go to the ISR, finish, and then come back. All right. So because of this nature, you want to spend a small amount of time, a minimum amount of time, okay, within the ISR so that you can go back and carry on with the loop. Okay, so with that sort of understanding, you can see that this, okay, is a potential a very dangerous way of coding. Why is that so? Because inside the interrupt service routine, you have a loop. So you can see that this is basically a loop. Okay, where you have to keep waiting, okay, indefinitely until this output device is ready. It could be the disk drive, it could be another port, something. Okay, so you are basically waiting indefinitely, okay, until the device is ready, because you want to write to the device, and then only you are able to exit. Okay, and why is this an issue? Because what if there is some issue with the output device? Okay, like it is stuck in some error state, or for some reason it is just not giving you the correct flag that it is ready. Okay, then there is a potential issue that you are stuck here for a very, very long time, or even indefinitely. Okay, and if you are stuck in the loop, that means if I write my ISR with something like this, okay, this kind of a approach, then there's a chance that I'm actually stuck somewhere in the ISR. And if I'm stuck in the ISR, I cannot go back to my main code. And if I cannot go back to my main code, then the whole system will just crash. Okay, so you should never have a loop inside the ISR that is conditional based on some external event or trigger or flag or anything like that. Okay, because then if that particular condition is not met and you are potentially in this never-ending loop, okay, then it becomes a huge issue to resume back to the main loop. All right, so this is a strict no. Okay, you should never have such architecture inside ISR. Okay, I mean, a simple example is that you can think of this as maybe your camera. All right, I say you when you take out a handphone, when you press the button, the camera button, okay, you want to trigger and take a picture. Okay, of course, once you take a picture, it needs to save to the memory, right? It needs to save to the memory. Okay, now if let's say every time I take a picture, okay, it processes the picture and the writing to the memory takes 6 seconds, 7 seconds. Okay, before you can come back and take the next picture, you will be very frustrated because 6-7 seconds is a lot of time. Okay, when you have your camera out, you want to quickly capture as many pictures as you can because the moment is at that time. All right, so waiting 5 seconds, 6 seconds is a lot. Okay, you want to immediately keep taking many pictures. All right, so the way in which you should handle it. So now we're going on to part B, right? So in part B, they're asking us how can I improve the overall design? Okay, so coming back to this camera idea, if the camera is the one that triggers the interrupt, okay, so of course once I trigger the interrupt, I need to first capture the picture, but that part can't be helped. I capture the picture in the interrupt, but the actual maybe back-end processing, compression, file system, all this other stuff, I should be able to carry on after that, okay, in the main loop, because the data is already captured. The raw data is captured, only the processing and saving is done separately. Correct. So what I can do is inside my system, I can, after I capture the raw data, okay, maybe even the processing I don't need to do. Once the raw data is already captured, I can set some flag. Okay, I can set some flag, all right, such that when I resume the main while loop code, I check for the flag. Okay, when I check for the flag, I know that this has occurred, and then I can do the rest of the stuff over here. That means the processing of the data, saving to the file system, everything. Okay, so you need to, or the way you need to approach the use of interrupts is, interrupts must always be very short and simple. Okay, I mean short and straightforward. Okay, directly to what you really need to do at that time. So if it's a camera button, what I really need to do at that time is to make sure I use the camera to capture the raw image first. Okay, then the backend processing, compressing, using the file system and the hard disk, everything can be done in some other place. Okay, so of course, if this was a multi-threaded system, it's a lot easier, correct? Because it's a multi-threaded system, instead of using a flag, I can actually use some other OS mechanism, okay, which we will be actually looking at. I mean, one of it we already studied, which is a semaphore, okay, or other things such as queues, message queues. Okay, so I can take the data and send it over using a queue, a message queue to another task. Okay, and the other task can then take the data and process it and write to the hard disk and so on. Okay, so it's a lot easier to manage, okay, the whole system with multitasking. Okay, or OS-based architecture. Okay, why? Because even though I have a flag, I have this idea of using a flag, there is still one other issue, right? Because the code that checks for this flag, where is it? It could be here, okay? It could be here, it could be here. We do not know where is the code that checks for the flag to do the processing. All right, so because the ISR could have happened anytime, it could be that I just miss the flag, the checking of the flag. So I need to go back to one full cycle before I can do it one more time. All right, so it is still not a very effective system. I mean, it may still work. The only thing is the real-time nature is not there. Okay, so I may capture the data, the camera data, okay, but the actual processing and saving and all might happen a bit later, okay, because of the loop, okay, the while loop taking time to go back. Whereas if I have an OS-based system, okay, I can use some other mechanism within the OS to take this data and send it across to another task or signal another task to process this information and so on. Okay, so that is basically the concept of this first question. Okay, so first you understand that ISR themselves have this limitation, okay, that you wanted to keep it short, and then at the same time, okay, you have a better way of doing it, but it's still not really ideal. Okay, but of course, having said that, I must also say that when you learn OS, of course, you feel that, okay, it's a very useful system, it's very powerful. I can really create a lot of very nice, or I can create a very nice architecture that is scalable and so on. Okay, but again, comes back to the very important question is whether does your solution or your system really need an OS. Okay, so just because we learn OS doesn't mean that you should straight away use OS for everything. Okay, because sometimes the complexity of the system is not so high, correct? And even without an OS, you can actually make it work. All right, so it's all up to how you want to sort of relate to the OS and get it to work. Okay, so for those of you, just to share, if you have done some hardware before, okay, let's say especially Arduino, okay, so I think most of you know what is Arduino boards. Okay, so if you have used Arduino boards before, okay, you know they're very very easy. Anybody can pick it up and start to put things together and develop a system and things like that. Okay, so Arduino of course has a lot of different sort of boards under them: Uno, Mega, Nano, and so on. Okay, and if you are of course doing this as a hobby or maybe even in your work or so on. Okay, if you are interested to port or use the Arduino boards with the OS, okay, what you can do is you can look at this thing called free RTOS. Okay, this free RTOS is actually a free OS, so it's an open source OS, and they have a port of this for a few of the Arduino boards. Okay, and they also have it for a lot of other boards as well. Okay, so if you are in that area or you just play around for fun, okay, then if you can also try the free RTOS on many boards as well. Okay, so again, this is only if you are keen to sort of look at how OS can be used on a more of an embedded platform instead of a general purpose system. Okay, so again, all these answers don't need to copy down. I will send you all this, I'll upload this later. Okay, the entire answer sheet here, and as well as this OneNote document. Okay, so you don't need to actually copy down anything. All right, as long as you listen and you understand the concept, I think it's fine. All right, so the next question is a semaphore and a mutex. Okay, are they the same? Okay, are they the same? So for this, we need to look at when and where do we use mutex? All right, so the concept of the mutex comes back to the lock and key. All right, so basically, when I have what we call a critical section of the code. Okay, so what is a critical section of the code? That means it is a section of the code where once I start, I want to make sure that until I finish that section, nobody else should have access to that data that I'm dealing with. Okay, we cannot prevent the multitasking and the context switching and so on. Okay, so you may still be in a situation where I am context switched out. Okay, so if I have task 1 that is running, okay, and then task 1 is the one that starts accessing the critical section. Okay, there's always a possibility that halfway through, okay, while I'm running, suddenly there's a context switch. Okay, and then the task 2 takes over. Okay, the key thing is, even though another task takes over, I should not allow another task to have access to this critical section of the code. Okay, that means whatever variables or data that I'm currently dealing with. Okay, so that is where the lock and key concept comes in. So the whole idea of Mutex is, before I enter the critical section, I lock it. Okay, and then I unlock it. Okay, so of course, lock and unlock is just a pseudo term. Okay, within the OS, you use the correct term, right? Which is Mutex lock and Mutex release or Mutex unlock. Okay, so it is basically that when I lock the Mutex, I am saying that I'm the only one who's having access to this critical section, and anybody else who comes after that, if they try to lock, they will be blocked. Okay, they will be blocked and they can't carry on. Okay, but if you recall, okay, last week's lecture, the last part where we did the demo and we had some changes in the code. Okay, so you would realize that this mechanism of using Mutex only works when everybody follows the rules. Yeah, everybody follows the rules. That means if I say that task 1 is supposed to lock and then enter and then unlock, then task 2 or task 3 or anybody else who wants to access the same critical section must also follow the same rule. So if I have another task that comes in, okay, but this other task does not follow the rules, okay, and it takes over the CPU, and later on it just says, okay, I want to access the critical section, but this task 3 does not follow the rules by trying to lock. Because the moment you follow the rules, okay, to say that to access this critical section, I must lock the Mutex, all right, automatically everything is taken care by the OS, because the OS will ensure that if somebody else already has locked it, you can't lock it, so you will be blocked. Okay, but if I don't follow the rules and I go ahead to access this critical section, then all the data corruption will happen. Okay, so this concept must be very clear to you, that the OS follows the rules strictly, but it is up to the programmer to implement those rules strictly. Okay, because the OS does not have any idea why you created a mutex. Okay, it has no idea why you created a mutex. It only knows that if I create a mutex, if the code tries to lock it, if it's available, you will get it, you can carry on. If you try to lock it, but it is not available, then you'll be blocked. So those are the very simple rules. Okay, so we just need to make sure that everybody who is supposed to use mutex to access this particular shared data, okay, does it correctly. Okay, then everything is correct. Okay, so the mutex general idea is this: protect a shared resource. For a semaphore, okay, it is to do two things. Okay, so one is of course manage resources. Okay, handle multiple instances of a resource. Okay, so this example you can look at it from the lecture slides, right, where we say that if I have maybe 3 units of resources. Okay, so of course when you say resource, what does it mean? Okay, it can mean anything, correct? It could mean that maybe my entire free memory space. Okay, I have 3 blocks of memory space that I can use. All right, so you can think of it that the amount of memory you have inside your phone, for example. Okay, to run an app. So whenever I run an app, okay, before I can run the app, I need to secure some memory. So the first app you launch, you secure some memory. Okay, then you can run. Second app that runs, it secures another chunk of memory, it runs. The third app that runs, it secures another chunk of memory, it runs. All right, so every time I take, I decrement. So 3 become 2, become 1, and then become 0. Okay, so if I try to launch another 4th app on my phone, okay, it will not allow me to launch because it says they got no more memory. Why? Because all the memory chunks have already been used up by the earlier apps or the earlier applications that launched. All right, so semaphores are useful, okay, in this scenario where you are trying to manage resources. Okay, we're trying to manage resources. Okay, of course, there is also another use case which is to synchronize different tasks. Okay, synchronize the flow of execution of different tasks. Okay, there's this one. When we do the message queue demo later, you will see how it works. All right, so even though we can still interchangeably use semaphore as a means of locking and unlocking. Why? Because if my semaphore count is 1, then it becomes similar to that of a mutex, correct? Because whoever take will become 0. So the next person who want to take cannot take. All right, and they have to wait. So it become blocked. Okay, until the first person return back become 1, then you can take. Okay, so the idea of a semaphore being used in the context of resource sharing or resource protection is also something you can do, okay, but it is not recommended. Okay, generally we use mutex and not semaphore. Okay, again there is another reason, okay, which is what we call the priority inversion. Okay, that one later or maybe next week we'll talk about it. Okay, about this priority inversion issue, okay, and why we need to handle this correctly. Okay, now, okay, so that sort of gives us an idea. Okay, so even though mutex and semaphores may seem similar, okay, there is actually a difference in the use case for each of them. All right, so it's always important to stick with the idea of why we need to use a particular. It's just like when you build something, correct? You have a toolbox. Okay, you use the correct tools for the correct thing. Okay, if you have a hammer to hit the nail, as you use the hammer, it will work correctly. Okay, if you use a plier to hit a nail, also can. Okay, it will still work. Okay, but it's not the ideal solution, even though it will work. All right, so the mutex is for critical section protection, whereas the semaphore is more for resource management. Okay, so let's move on to the next question. So in this, they have asked us, okay, 2 or more threads want to communicate. with each other by passing information through a common data structure. Okay, give two examples of such data structure. Okay, so one of the data structure again that you are already familiar with is the concept of a global variable. Okay, so if I have a global variable, okay, let's say integer x. Okay, so anybody can function A, function B, or task A, task B, anybody might be able to access this global variable. All right, and another sort of structure that is used for communicating is what we call the message queue. Okay, so a message queue or task queue. All right, so there are two different variations which we will actually cover that later today. All right, so these are some of the data structures that are used. All right, so this concept of global variables, of course, all of us know, and sometimes we are tempted to use global variables for everything. All right, because it just makes our life in a sense easy, correct? Because everything I declare as global, going to pass anywhere, going to retrieve anywhere. Okay, but again, global variables, the use of them should be very carefully managed. Okay, in some development teams, okay, they may be having very strict rules about the use of global variables. Okay, so you can't just freely use them. Okay, so even in your own personal project, yes, you may want to think that that is a better, easier option. Okay, but in a more sort of a development environment setting in a company or so on, okay, they may have very strict coding guidelines where they restrict, okay, when and how you should use global variables. Okay, and the reason is very simple, right? Because once you declare a global variable, even though one part of it makes your life easy, anybody and everybody can access that data, which means that the chances of it getting corrupted and affecting your system is very high. Okay, so as much as possible, we want to avoid global variables. Okay, and use other mechanisms for tasks to communicate with each other. Okay, so that is where the task queue and message queue comes in. Okay, which we will be discussing later. Okay, so in this part B, they basically tell us how or a scenario, okay, where you have two threads, okay, both sending some information to this shared printer. Okay, so of course, if the data that is being received by this shared printer is not managed correctly, then what you have is you have garbage being printed out, right? Because everything gets jumbled up over here. Okay, so there must be a proper way for the printer that is receiving the data to make sure that everything is in order. Okay, so one way is, of course, we can always limit and control who is able to talk to the printer. Okay, so we can use the concept of a mutex. Okay, so if I want to send a print job, okay, I must acquire a mutex. So once I acquire a mutex, I'm the only one who is able to send a print job, and nobody else should be able to send a print job. All right, then of course, then anybody else who is wanting to send should be in the queue until I have finished sending my data. So the printer will only receive data from one particular task at a time. Okay, so that is one way. Okay, or we can also use semaphore, okay, or message queues or any other OS mechanism that we are studying. Okay, so all those mechanisms will work, okay, to make sure that the printer only receives data from one task and processes it before anybody else can send any data. All right, so of course this is a very common scenario in a multi-threaded environment, okay, because in a multi-threaded environment a lot of things are happening. Okay, but it can also happen in a single-threaded environment. Okay, so in a single-threaded environment, okay, basically what happens is you are having this concept of interrupts. All right, so even with interrupts, these things can happen, correct? Why? Because in my main loop, Okay, if I have a global variable integer x and I have a ISR, okay, and the ISR also is trying to access x. So here also I try to do something to x. Here also I try to access x. Then is also a issue, correct? So I need to also manage this correctly in a situation where the ISR and the main loop are trying to access the same variable. Okay, so of course you may need to have your own mechanism of using some flags to control access to this variable. Okay, so there's a question: is mutex using states? I mean, in the mutex, basically, if you think of it in terms of states, basically it is only two states. Okay, it's either is available or it's locked. Okay, so it is only two possible states of the where mutex can be in. So if it's available means the OS will give it to you when you ask for it. Okay, which also means that anybody else who wants it, if it's not available, they will go to a block state. Okay, so the concept of states, okay, again, maybe we might accidentally mix up some of this terminology. So in programming, in algorithm design, sometimes we call it a state machine design. Correct. So in that context, the term state is different. Okay. In that context, when we say state machine design, okay, we are saying that okay, I want to do a sequence of activities. Correct. Then I say state 0, state 1, state 2, state 3. Okay, and then based on the rules, I may say I go from here to here and then here to here and so something like that. So that idea of state machine design is how I want the software to flow, okay, a particular sequence. Okay, that is the way I intend, because okay, if I'm in particular state 1 and an input occurs and the input is a particular value, I go to state 3, if not I go to state 2 and so on. Okay, so that is the high level architecture, and you develop the code using that. Okay, in our OS, okay, in our OS, we use states, correct? But in the OS concept, we look at it as a state transition diagram. Okay, state transition diagram. So in the state transition concept or diagram, basically what we have is you have the three main states, which is the ready, the run, and the blocked. Okay, so this one we sort of covered that, I think, last 2 lectures back, right? The overall architecture of the OS. All right, so in this OS concept, when we talk about this state transition, it is moving the task from one state to another state. Okay, and again, all of this depends on the OS. So everything in this state transition is totally transparent to us. It's all managed by the OS. All right, so the OS will continuously check the ready queue and select the highest priority to go to run. Okay, if while I'm running, suddenly I cannot get something, I may be blocked. Okay, if not, I voluntarily give up the CPU, I go back to the ready queue and so on. Okay, so all of these things are managed by the OS. Okay, so it is different from the state machine design that maybe you have done before. Okay, because in the state machine design, when you come up with this architecture and you code it, correct? And you code it because you control the sequence. You decide that this is the sequence of events that will happen. Okay, but in the state transition concept of the OS, only the OS will decide. So our responsibility is to implement the architecture, the framework, okay, that will specify the rules, correct? So task A can run as long as it has the resources, okay, but if it cannot get something, it will be blocked until that resource is released and so on. Okay, so the rules of when a task should be able to continue, when it should be blocked, so those are the rules that we should implement in the code. Okay, and then the OS will handle everything else for us, okay, in the back end once you are running. Okay, so this question here. Okay, atomic operations. So what is an atomic operation? Okay, so I think we covered this. So atomic operation is basically something that is that you can complete, okay, without preemption. That means if I start it, I must be able to complete, okay, fully without getting preempted. Okay, so of course, if I have a chunk of code, I can't guarantee that, all right, because anytime I can get context switch out. All right, so if I have a chunk of code and I say this has to be treated as an atomic operation, okay, that means once I start, I cannot stop. I cannot let go of the data. Then you use the mutex. Okay, mutex lock and mutex unlock. All right, so that is the chunk of code concept. But if I have only a single line of code like this, okay, is this considered atomic? All right, so again, it comes back to relating to what we have studied in our assembly language programming, correct? That everything that we do has to be related back to the processor executing instructions using its internal registers, correct? So when we look at this b equals to 100, our understanding should now be very clear because we already done the first part. So we know that b is a variable in memory, correct? B is a variable in memory. Okay, so I want to have a value of 100 inside this variable, inside this memory space. Okay, but in order to do a memory access, I need to do a store word instruction. So we know that I need to store word. Okay, I mean, depending on which architecture you use, but just thinking of MIPS, we know that we need to do a store word to write a value to a register. Sorry, a value to a memory location. So when you do a store word, the source of the data is a register. All right, so I need to take the content, okay, from a register. Okay, so maybe this is register A0. Okay, and I need to take this content and I need to do a store word operation to write it to the memory. Okay, so of course, before I can even do the store word, I need to make sure that the register A0 has the value 100. Okay, so I first need to take a sort of a load of a value of 100 into my register A0. Okay, how you do it again comes back to the lower level assembly language and the architecture you are dealing with. All right, but this basically gives us the idea that I need to load a constant value to the register A0, and subsequently, once that constant value is loaded to the A0 register, then I can write it to the actual memory location that corresponds to the variable B. Okay, so this single instruction in C still translates to 2 steps in my assembly. Okay, so as long as it's more than 1 step in assembly, then you cannot guarantee that it will be complete, because any point of time between these 2 lines of code, I can still get preempted. Okay, I can still get preempted, which means I will do a context switch out. All right, and then by the time I come back, maybe things would have changed. Some other new value could be inside the A0 register. Okay, and then everything goes wrong. Okay, so this is not an atomic operation. So even though in C, we look at it as a single line of code, okay, in reality, it can be many lines of code in the assembly language. Okay, so context switching can happen anytime, okay, which means that I cannot guarantee this. Okay, so if I really want to protect this 1 line of code, okay, I still need to do a mutex lock and unlock. Okay, if really I need to protect this 1 line of code, okay, you still need to do a mutex.
Does the C compiler do that?
No. We have to do it manually. Okay, so you have to manually put in your own lock and unlock, okay, for any line of code, okay, that you want to protect. Okay, so that is again to highlight the whole idea of context switching, that we cannot predict and say when it will happen. Okay, we cannot say that. You can only implement the architecture based on the rules and understanding of the resources that the different tasks would need. Okay, and then from there, if the architecture is mapped out correctly, then of course things should work. Okay, but again, if it doesn't work, then we need to go back to see where it's breaking. Okay, maybe some task is not sending the correct data over. Okay, or you're not, or one task use the mutex, but another task didn't use the mutex, and so on. Okay. All right, so let's look at the last question here. So it is similar to the examples that we discussed last week, all right, where we have two tasks, okay, task A and task B, and then we are told that task A has a higher priority than task B, and the semaphore has an initial value of 1. Okay, so this is all important information. Okay, we need to understand what is the context of this code that we are looking at. All right, so the two important things is task A has a higher priority than task B, and the semaphore has an initial value of 1. So what will be printed out on the terminal screen? Okay, so let's look at this and try to understand the nature. Okay, so of course the best way to understand this is to draw out a state transition diagram. Okay, so let's look at it first. So you have task A, and you have task B. Okay, so since task A has a higher priority than task B, we know that task A will run first. Okay, so we can say that task A will run first. All right, so once task A runs, what do you see happening? The first thing that happens is it causes OS delay for 500. So once it causes OS delay for 500, that means over here, I'm going to say delay for 500. Okay, so once it goes to a delay, that means it's going to be a block state. Okay, it's going to be a block state for 500 milliseconds. And in that time, okay, so once the current task that is running goes to the block state, the scheduler will come in. All right, the scheduler will come in and it will look at who else is in the ready queue. So it knows that task B is in the ready queue, okay, waiting for a chance to run. So until that point of time, it was still ready. Okay, but the moment the task A went to a block state, I was able to do a context switch, and this one switched to the run state. Okay, so once it switched to the run state, what happened? Okay, it will start to run. So once it starts to run, the first thing it do is it tries to take the SEM pen. It tries to do a SEM pen. That means it tries to take the semaphore. So let's look at the semaphore. So the ready SEM. Okay, so we know that the ready SEM is equals to 1, the initial value. So if the initial value is 1 and I do a SEM pen, I will be able to get the semaphore. All right, so the ready SEM at this point in time will become 0. So the SEM pen is successful. Okay, once I take the semaphore, the ready SEM value will become 0. Okay, and then what do? I will print world. Okay, so this is what I will print. I will print the string world. And after that, what do? I post the semaphore. So the next step is I post the semaphore. So when I post the semaphore, what happens? I will increment the value. Okay, and since the current value is 0, I will increment and the ready will become 1. Okay, and then I go to call another block, another delay of 500. Okay, and once I do that, what happens? I will be blocked for another 500 milliseconds. All right, so of course, this 500, the task A 500 will finish first. So let's assume it finishes here. Okay, somewhere around here it finishes. Okay, while this is still going on. All right, so once task A finishes this 500 millisecond, it comes to this line and it says sampen. Okay, so since the current semaphore value is 1, okay, I will be able to take it. So okay, over here I transition to run and I call sampen. So since the semaphore value is 1, I can take it. So the semaphore value will become 0. And once I take the semaphore, I will be able to print hello. Okay, so come here, I'll be able to print hello. Okay, so once I print hello, what happens? Okay, once I print hello, what happens? I go back to the loop. I go back to the first beginning of the loop, which means I go back to calling my delay. So again, I start my delay. Okay, so I go to a block state for 500 milliseconds. Okay, so at that point of time, okay, somewhere along the way, your task B would have come out of the delay. Okay, and once it comes out of a delay, all right, what happens? You go to the so once you finish the delay, it comes out of the block state. All right, and since task A is also in the block state, you will allow task B to carry on. Okay, so task B will come out. So first you'll go to ready, and then I'll go to run. Okay, so once it goes to run, what happens? You will be able to go back to the top of the loop. And in the top of the loop, what does it do? It tries to do a sampen. Okay, but now what's the problem? The problem is that the task A took the semaphore, but it did not do a sempose. It did a sampen, but it did not do a sempose. Correct. So the semaphore 0, but it did not return the semaphore. So since the semaphore count is 0, when the task B tries to do a sampen, it will be blocked. Okay, because the value is 0. Okay, so the ready semaphore value is 0. So this was not going to be successful. So you will go to a block state, waiting for the semaphore to be updated, to be released. Okay, and task A that is currently blocked, eventually it will come out of the block state. When it comes out of the block state, since task B is ready, since it is a higher priority, okay, once it comes out of the delay, it comes back to this sampen again. Correct, and then it will try to, so once it runs, it will do the same thing. It will do the sampen. Okay, and then the same issue, correct, that the ready is 0. There is no semaphore. So again, it will be blocked. Okay, so it will stay in a block state. So eventually what happened? Both the tasks stay in a block state indefinitely after that. Okay, indefinitely after that. Okay, so basically what you will see being printed out is you will see world and then hello, and that's it. Nothing else. All right, and the reason why nothing else is because your task A took the semaphore but did not return it. Okay, did not return it. So this is again sort of showing you that if you don't use the OS sort of tools correctly, okay, then again the behavior may not be what you expect. Okay, in some cases, yeah, maybe you only have one task that do a post, one task that does a pen, all right, which we will see later, all right, in the message queues. But in some cases, maybe you intend to do sampen and sempose, okay, before and after, but maybe one task it did, but the other task did not do it. Okay, and then the whole sequence gets messed up. Okay, so that is basically the last question for this tutorial. All right, and as you can see, when you see this kind of questions, you must always understand the context. Okay, how many tasks there are, which one is the higher priority, which one is the lower priority. Okay, and what whether it's a semaphore or a message queue or whatever, what are the initial values? Okay, what are the initial values or the state of the system? Okay, when you are going to examine the behavior of the code. Okay, so does anybody have any questions you want to ask about this tutorial? Okay, so I think so far no, but again, no issues. If anytime you have any questions, you can always put it in the chat. Okay, and we can discuss this further.
Actually, I have a question about question 5B, I think. Is it 5B? Oh no, it's 5A. So I noticed that the question states it's a multi-threaded environment.
Yeah.
Yeah, so I was actually under the impression that in a multi-threaded environment, task A and task B can run simultaneously.
Yeah, I mean that's the idea of multi-threaded environment, correct? That the tasks run concurrently, but the term concurrently is used to describe the environment, but in reality we have the understanding that at any point of time only one task can run, correct? Because of the OS managing the states of the task. Okay, so even though we have many tasks, at any point of time only one task can be in the run state, the rest of the tasks will be either blocked or in the ready queue. So with that, okay, and since we know that task A is higher priority than task B, then we start off with task A running first, and then we examine how the code will execute.
Okay, thank you.
Okay, so yeah, so this concept of multi-threading is, again, we say it is concurrent, okay, we say it's parallel, okay, but all of that is just a descriptive term. Okay, in reality, we still come back to the understanding that there's only one task that will be in the run state at any point of time. Okay, and everybody else could be in the ready queue, some could be in the block state, again, all depending on what you are trying to do or how the architecture is designed. Okay, so that sort of wraps up the tutorial. Okay, so in terms of the lecture slides, okay, where are we now? Okay, so we are basically last we stopped here, okay, for the mutex and semaphore. Okay, so I think right now will be a good time to go for a break. All right, so what we will do is we'll go for a break now. Okay, now it's 7:30, so we'll take about 15 minutes break. Okay, when we come back, okay, I think 7:45, what we will do is we will finish up the rest of the slides on the message passing and the queues. All right, and then I will do the demo on that. Okay, so again, there are two demos I want to show, one on message queue and one on task queue. So we will see how is the timing, and then we will try to either do both today, or if not, we'll do one today and then the other one next week. Okay, so we'll go for a break now. Okay, we come back at about 15 minutes time, and then we will look at this message passing concept. Okay, so in the meantime, you have questions, you can just put it in the chat. Okay, later we will come back and then I will address those questions. Okay, so I'll see you all back here in 15 minutes time. Okay, so welcome back after the break. So let's finish up our slides. All right. So last we talked about. Let me share screen. Okay. So the last we stopped was when we were talking about mutex and semaphores. All right. So these are usually the first two things that you will always learn about whenever you're going to pick up any OS. Okay. So every OS out there will definitely have this concept of a mutex and semaphore. Okay, but there could be some variations or some features that some OS has that some don't have, and so on. Okay, so usually it's always good to go through the OS documentation in detail, okay, to understand exactly how it may be different, okay, from what you are used to. Okay, so it may behave in a similar way, correct? But there could be some maybe tweaks that you may do that you don't actually see happening in other OS. Okay. So besides mutex and semaphore, the next thing is what? The next thing is how can I communicate through message passing? Okay, because when I use semaphore and I use mutex, okay, so with semaphores, you can also synchronize the flow of the task execution. Okay, that is one way, but there is still no way of passing information directly from one task to another task. All right, so that is where this message passing concept comes in. Okay, where with this message passing, it is actually you're doing two things at the same time. Okay, one is I'm actually having the transfer of data, and at the same time I'm also able to synchronize. Okay, so this is actually a very, very useful way of making or accomplishing both these tasks together, data transfer and synchronization. So generally, we can say that we have two basic forms of message passing functions, which are the send and the receive. Okay, so of course there are a lot of variations around how send and receive may be implemented. Okay, so that is what we're going to look at, okay, in terms of the variations and what the OS or may support and may not support. Okay, so one of the way in which synchronization is achieved, okay, between sender and receiver is that the receiver is blocked, okay, waiting for a message. Okay, so in this example, what happens is task A and task B. So if it happens that, okay, so in this case, task A is sending the message and task B is supposed to receive the message. Okay, but what happens if task B runs first? Okay, task B runs first and says, okay, I want to receive the message, but there is no message yet, because task A has not had a chance to run until that point to actually send the message. So if this scenario happens, okay, and task B has to receive the message, because based on the received message only, it will know what to do. Okay, so in this situation, what we will say is that the receiver is blocked, waiting for a message. The receiver is blocked, waiting for a message. That means if task B is called first, okay, and there is actually no message yet, okay, sent over, then I will be blocked, waiting until the message is eventually sent. And once I receive the message, then I can be unblocked. Okay, so that is the receiver waiting for sender. Okay, so how does this message passing work? Okay, the general idea. The general concept is when you want to send messages from one task to another task, you first need to create what is called a queue. Okay, so you can think of queue as a buffer, all right, or just an array where you can store this information and send it across. Okay, and of course, when you send information through this queue, you don't need to populate the entire queue. Right? As and when you send, the receiver can also progressively retrieve the data. Okay, so if I have a queue, like in this case, I have a queue of size 5 and it's equals to 5. It doesn't mean that I need to put in 5 elements, then only task B can take. No. The moment the first element goes in, task B can take. It all depends on when task B attempts to read the queue. Okay, so in this example, what is happening is the task A is writing to the queue. So first it writes a value of 10 to the front of the queue. Okay, and then it wants to write something else, so it also updates the queue. Okay, so each of this case, what's happening is we are transmitting data, okay, by updating the queue. So by updating the queue, that means technically we are sending data. All right, it's just that task B may not have received the data yet. But when task B calls to receive the data, it will also receive in the order in which it was sent. Okay, or the order in which it is stored in the queue. Okay, so if the first data in the queue is a value 10, then that is the first one that will be retrieved. After that, the second element will get pushed up. Okay, and then the second element will take the first element's position. And subsequently, the next time I try to do a receive, I will receive this data. Okay, so basically what happens is whenever the sending task wants to send, it will update a new slot in the queue, and the receiver will extract from the front of the queue. So the moment it extracts the first data, everything else in the queue moves up. Okay, so all of this is of course managed by the OS. We don't need to worry about managing this queue. Okay, what we need to do is just make sure that the tasks that are supposed to send and receive do it correctly. Okay, so in this concept, basically what we're trying to say is the data is the actual data in the task A is still there. Okay, and task B is receiving a copy of the data. Okay, a copy of the data through the message queue. Okay, that is what the concept is trying to be illustrated here. Okay, now in terms of naming schemes or naming convention, again, this could be different across different OS. Okay, just give me a minute here. Okay, so in terms of this naming schemes, there is two types. All right, one is what we call a direct, all right, where you specifically say that who you are sending it to. The other one is the indirect, where you can have a generic mailbox and a lot of people can actually access it. Okay, so let's look at this. So in terms of a direct naming scheme, what it means is that I can take one task, okay, directly send to another task. Okay, now in terms of indirect, what is happening is the task that is sending might send it to what we call a generic mailbox, and anybody who wants can read from this mailbox. Okay, can read from this mailbox and then extract the information. So again, in which mechanism or which technique you use all depends on what you're trying to do. What is the architecture? What you're trying to achieve, and who are all the different tasks involved, and so on. Okay, so there is no sort of discussion of what is better or not. Okay, both of them are equally good. It just depends on the scenario, the application. Okay, so in the direct naming scheme, of course, you need to know the process ID, or in this case, the task ID of who you are talking to. Okay, it's just like when you call somebody, right? You need to know that person's name and the number. Then you know that I can call this person or message this person. Okay, if it is somebody you do not, you put in a general group, then what happens? Then everybody can read the same message. Okay, can extract that information. Okay, so in the indirect scheme, it's like putting a message inside a group chat. Okay, where anybody who has access to the group chat can retrieve that information that you share. Okay, whereas if you directly send to somebody, then you must know who you're talking to. So of course, all of this comes back to a lot of different ways of one-to-one, many-to-one, and so on. Okay, but again, these are all just ideas. Okay, as long as you have a concept and you want to implement it, you need to look back at how that message queue or mailbox is implemented, and then you can use it. Okay, so in terms of the blocking receive or non-blocking receive, okay, what is the difference? Okay, in terms of blocking receive, what happens is the receiver must wait for a message if it is not already available. Okay, so like what I showed you just now, if the receiver calls first, okay, this is A and this is B. If the receiver calls first, receive, okay, but there is no data yet, then I'll be blocked until a point of time when the A send the data. Then I'll be unblocked and then can run. Okay, so the receiver, if it's a blocking receive, then the receiver must wait. Okay, then of course there is also the option of a non-blocking receive. Okay, in non-blocking receive means you don't wait. Okay, then of course the question comes, if I don't wait, I don't have the message, then what do I do? All right, so that is where your code needs to factor in both these scenarios. Correct? That means I try to take the message, or try to retrieve a message, but nobody has sent me the message. Okay, so if I get the message, what do I do? If I don't get the message, what do I do? Okay, so that is again something that you need to implement in your code. Okay, generally I would suggest that using blocking calls are a lot better. Okay, a lot better. Why? Because that enforces the sort of sequence. All right, the synchronization between different tasks. Okay, because if you do not do this, then what happens is the task can just carry on, and then you need to look at all the different possible scenarios. Okay, in some cases it can get very complex. Okay, so it's always easier to have a blocking call. Why? Because then I know for sure that I will only continue to the next part of my code if the data has been received. If there's no data, then there's no point. But I won't be able to. There's no point in me carrying on and trying to do anything else. Okay, same thing for asynchronous. Either the sender is never blocked. Okay, if the receiver has not yet executed the message received. Okay, again, in this the system buffers the message. All right, and then you can retrieve it later on. So this is an example. So in asynchronous, the message task B calls the receive first. Okay, after it calls the receive, if there is no message, I need to be blocked. Okay, until a point of time when the message is sent over. When the message is sent over, then I unblock. Okay, then I can ready and run. Okay, but in the case where the sender sends the message ahead of task B running, the task A runs first and it sends the message. Okay, and it can actually carry on until task B retrieves the message. Okay, so when task B retrieves the message, then you can decide on the next state. Okay, depending on the priority and the state of the other tasks and so on. Okay, so this again concept of sending and receiving is because we are able to declare this buffer size. So when you send a message, receive a message, it's not just a single message. It's up to us to define how big this buffer size is going to be. Okay, so if we want to have more messages, then we just declare a bigger size. Okay, the last part here is basically the synchronous message passing. So what is synchronous message passing? So in synchronous message passing, basically the sender is also blocked until the receiver receives. So it has to match. Okay, so in this case, okay, when the sender happened to send first, okay, but the receiver has not received, then the sender has to be blocked. The sender will be blocked until upon time when the receiver has already received. Then I will send the next message. So this sort of allows you to have a smaller buffer size, correct? Because you can't fill up the buffer with more data. Okay, every time you fill up the buffer with some data, the data must be read from the receiver side before you can do anything else. Okay, so that is the synchronous message passing concept. Okay, so that sort of gives us the overview of the message passing. Again, that is a general overview. Now let's look at exactly how the OS, microchip OS3 does it. So all of this we already saw, okay, last week, semaphore, time delay, everything. Now, in this demo, we also see. So let's look at the message queues in the OS that we are dealing with. Okay, so the message queues is basically, again, the implementation details are specific to the OS you're using. Okay, so the first thing is the message queues are in a first in first out pipe. Okay, which means that the first message that you send will be the first message that is also received or retrieved by the receiver side. So in terms of message queue, okay, so the first thing I need to do is I need to first create a new message queue. Okay, once I create a new message queue, then the task can either post, okay, to the message queue, while the task that is expecting to receive the message, you will receive by calling OSQ pen. So OSQ post and OSQ pen. Okay, so the advantage of this message queue is what? The advantage of message queue is that you can have multiple tasks waiting on the messages. Okay, so what is only a multiple tasks can wait on a message queue. Okay, so if so many tasks are waiting on a message queue, then who gets the message? Correct. When somebody sends over, who gets the message? The highest priority task waiting on a message queue will receive the message. Okay, so that is how the message queue system works. Okay, so the message queue is, again, think of it as a general mailbox. Okay, where anybody can post data to it. Okay, and of course the most important task, okay, which is able to run will be the first one to access this data in the mailbox, the very first data, and then subsequently and so on. So of course this may be a good option for some of the applications. Okay, the other alternative, okay, which is also very useful, is the direct naming mechanism. That means instead of putting everything in a generic message queue, I want to directly send to a particular task. Okay, I want to directly send to a task. Okay, so in this case, what happens is I not only simplify my code, but it's also more efficient. Okay, using just the message queue. Okay, which I will show a demo later. So what are the things we need to look at for message queue? Okay, so the first thing is we need to create a queue. Okay, so inside the code, the first thing is we need to first create a queue by calling OSQ and giving it a name. Okay, now the next thing is I first have the variable name and then I create the queue. Okay, so when I create the queue, you can see here that I actually need to specify the size. So this is the maximum number of messages that it can receive, okay, inside the buffer space. Okay, so in terms of this message queue, okay, the code. Okay, so what is the code doing? So this is the code from task A. So what is the code trying to do? So it's first calling OSQ post. Okay, what is OSQ post? When I say OSQ post, that means I want to push some data onto the buffer. Okay, so this data is actually this. So this is the actual data that I want to push onto the buffer. Okay, and which buffer? This is the buffer, the myQ. Okay, so I'm going to push data into this buffer called myQ, and the data is actually this variable called count. Okay, and the rest of it is just the additional protocol for the implementation. Okay, so the message size, error, and all this thing, we can just keep it as it is. All right. Now, once I execute this, what happens? That means in the message queue, I put in one element, which is the variable count. Okay, I have put in a message into this buffer, which is called count. And what I want to do, okay, so in this example, okay, which we'll see in a while, I want task A and task B to actually talk to each other, okay, by sending messages to each other. So task A will put a message onto the buffer and task B will retrieve, and subsequently task B can send and task A can also receive. Yeah, because the whole idea of message queue is it is just a generic buffer. Okay, so anybody who knows this buffer's name can actually send to it or read from it. Okay, so that is the first one. Now, before we look at the semaphore line, let's look at the next one over here. Okay, okay, so maybe we should look at why we need to use a semaphore. Because what I want to do, okay, in this example here is, we have this variable called count, and I want to send this variable count over to task B. Okay, I want the variable count B to do a increment by 1. Okay, and after that, the task B can send the data back to task A. Okay, using the same message queue. That is the objective. Okay, so this example, the objective is this. Okay, task A will take this variable count, send this variable over to task B. Okay, task B will increment this variable by 1, and it will send this updated value back to us. Okay, now with that understanding, we know that in order for me to send from task A to task B, I must do a post. Okay, I will do a post. Now, when I expecting the data to come back to me from task B to task A, I need to do a pen. Okay, so first the task A will post to task B. Okay, task B will increment the variable and task B will send back. Okay, so since I know that task B is going to send back, task A is waiting for the data by calling uC-OSIII, okay, which is here. Okay, so why do I need the semaphore? Why do I need the semaphore in this case? So this line here, I created a semaphore, the same semaphore we have been using before in the labs. Okay, and I say sempen. Okay, sempen means I'm waiting for a semaphore. Okay, so why would I want to do this here? Okay, why can't I just send and then I receive and so on? Okay, why must this semaphore suddenly come into the picture? Okay, the reason is, okay, because of the fact that when task A is running, okay, when task A is running, okay, what happens is, if I don't put a semaphore, what happens is task A will do a post. Okay, and after that, it will straight away do a pen. Okay, it will do a post and then it will straight away do a pen, which means that it is similar to say you pass from the right hand to the left hand. Okay, so the data will immediately come back to you. Okay, instead of having a chance for task B to run, the data is always stuck within task A. Okay, because I put onto the queue, but immediately after I put on the queue, I say I want to do a uC-OSIII pen. So the data comes back to me. Okay, so that is basically one of the issues with using the standard queue. Okay, standard queue, because in the standard queue, you need to look at all of this. Okay, this issue here. So that is why we need to put the semaphore. So over at task B, what is happening? Okay, over at task B, what is happening is the task B is calling the OSQ pen. Okay, so calling OSQ pen. That means when task B gets to run, it is expecting data to be sent over. Okay, sent over by task A. Okay, and once it receives that data, okay, it will be able to print it out. So that received data will come here, and then it will print out that received data. After it print out, it will do a increment. Okay, and after it does the increment, it's supposed to send back. Correct? Task B does the increment, it's supposed to send back to task A. Okay, so after it does the OSQ post, it immediately posts the semaphore. Okay, it posts the semaphore. Why? Because task A has been waiting for the semaphore. So currently task A is still here. Okay, so the moment the task B posts the semaphore, I will be able to retrieve, and since task A is higher priority, I'll be able to run. And then the task B already posted something on the queue. Okay, already posted something on the queue. So when I call this OSQ pen, I would already know that somebody has already posted something for me in the queue. So I can immediately take the value and I can print it out. Okay, I can immediately print it out. So let's see this in action over here. Okay, so this is the code, okay, for the message queue. Okay, so if you look here, what you have done is like what we have mentioned. We have created a message my queue, okay, with the OSQ data type, and we have also added a semaphore over here. So again, this semaphore is because there is nothing else happening between the send and the receive for task A. Okay, if there were other things that you needed to do, then maybe you don't need a semaphore. Okay, but since we are not doing anything else, we want a semaphore to ensure that the sequence is correct. Okay, so everything is as per normal. Okay, we have the OS, we have the main, okay, that creates the startup task. So this is same as before. You create a startup task, and at the same time, I do two other things. I create the semaphore by calling OS sem create. Okay, so as you can see, I initialize, okay, it to 0 first. Okay, then after that, I create the message queue over here. Okay, and once I do that and I call OS start, what happened? The task A will run. Okay, so in the startup task, the startup task will run. Startup task runs, it will create task A and task B. Okay, so this is exactly the same as last week. So last week we did the same thing. We have the startup task, and startup task will create task A and task B. So task A and task B are here. Okay, and if you look at task A and task B, once they have been created, okay, so what happens is you will get to run task A first. Okay, so maybe let's step back a bit here. Okay, so this is the message queue. Okay, so let's again visualize what's happening, so it'll be easier. Okay, so we have the main, okay, they call the I just want to get the correct name, the startup task. Okay, he called the startup task. Okay, so once you call the startup task, okay, then what happens? Okay, once you create the startup task, okay, so maybe I should not draw it that it calls startup task. Okay, it's the wrong idea. So we should say that it create startup task. Okay, because we don't call tasks. We don't call tasks. The OS handles it. Okay, so we create the startup task. Okay, and after that we create semaphore and create the queue. Okay, so we say that we create semaphore and create queue. Okay, create semaphore, create queue. Once I do that, what else am I doing here? I start the OS. So if you look at the sequence, you will know that the moment I call OS start, I switch from my single-threaded sequential environment to the multi-threading. Okay, so at this point of time, I already start the multi-threading. Okay, once I call the OS start. Okay, so let me write this properly. So here, what I do is I create the semaphore. Here I create the queue. Okay, and then here I say OS start. So once I say OS start, it will immediately switch to the multi-threading. So I will never come back to the main. Correct. So I switch to multitasking. All right, and once the multi-threaded environment kicks in, the scheduler will come in and it will see, okay, who is available. So since I have created this startup task, okay, and that means that's the only task in the ready queue, I will be able to run the startup task. So the startup task will run. Okay, so the startup task runs, and what does the startup task do? Okay, so it does two important things. It creates task A and it creates task B. Okay, it creates task A, creates task B, and then it just delays forever. Okay, so that is the same thing that we're going to do here. We're going to create task A, and then we're going to create task B. Okay, and again, once we create task A and task B, it goes into a delay, an indefinite delay. Okay, so it is permanently blocked. So since it is permanently blocked, okay, then again the same thing happens. Correct? The scheduler will come in. It will look at, okay, who is in the queue. Okay, who is in the queue? So you can see that both task A and task B are in the ready queue. Okay, both task A and task B are in the ready queue. So since both of them are in the ready queue, what it will do is, since it will look at the priority. Okay, so if you look at the app-config.h, okay, you can see that task A is higher priority than task B. Okay, so since task A is higher priority than task B, what happens is it will schedule task A to run first. Okay, so task A will run first. Okay, so task B is still there, but it's in the ready queue. Okay, so we'll just put it here. So task A will start to run. And once task A runs, what does task A do? Okay, it does what we saw just now. It puts a message on the queue and waits for semaphore. Okay, so that's what I'm going to draw here. Okay, so you say queue put. Okay, so I put a message on the queue. Okay, and once I put a message on the queue, I also call sempen. All right, so since the semaphore, okay, coming back here, the semaphore initial value is 0. All right, semaphore's initial value is 0, is what we saw just now here in the main function. Okay, initial value is 0. So since the initial value is 0, when the task A tries to take the semaphore, it will say that the OS kernel will say that there is no semaphore available, so I need to put you in a block state. Okay, so because of that, this will go to a block state. Okay, so task A goes to a block state. Then what happens? Okay, so we know that task A already posts a message to the message queue. Okay, but nobody has retrieved it. Why? Because task B has been in the ready queue for all this while. Okay, until here. Okay, so until then, task B was in the ready queue, but the moment task A went to a block state, okay, it was able to switch over. Okay, so once I'm able to switch over to task B, then what happens? Let's look at task B. So what does task B do? The moment it can run, the first thing it does is it calls uC-OSIII pen. Okay, that means it expects to receive the data. Okay, so the very first thing that it does is it calls uC-OSIII pen. Okay, and when it does uC-OSIII pen, that means it wants to read from the message queue. Okay, and task A has already put something in the message queue. So when I do this OS message queue pen, I already am able to immediately get the data. So there's already data there. Okay, so since there's already data there, I am able to retrieve it and just carry on. Okay, so when I carry on, what do? I increment my variable by 1, and then I post it back to the queue and post the semaphore. So let's do that here. So what task B is going to do is, first it's going to do the plus plus. It's going to increment the variable. After it increment the variable, it's going to call semaphores. So when you call semaphores, what happens? Okay, the message goes into the queue. Okay, the message goes into the queue. Okay, and immediately after semaphores, what does it do? It calls the sorry, this is not semaphores. This is the message queue post. It posts the message. This is the uC-OSIII post. Okay, after that, then it calls the semaphores. Okay, so what does the semaphores do? It will release the semaphore. Okay, it will post a semaphore. That means it will attempt to increase the value. So the current value is 0, but there is already a task that is blocked. Okay, so since the task is already blocked waiting for the semaphore, okay, then what happens is the moment I call semaphores, so the moment I call semaphores, yes, I will immediately be able to take that semaphore that is being posted and assign it to the task A. So which means the task A will be unblocked and it can transition to the run state. Okay, it can transition to the run state. And once it transition to the run state, what happens? Okay, once task A transition to the run state, that means it is able to get the semaphore. Once you can get the semaphore, means it calls the uC-OSIII pen. Okay, so when it calls uC-OSIII pen, so in this case, first thing it does is it gets unblocked, so it goes to the ready state, and then it calls the sem pen, uC-OSIII pen. Sorry, uC-OSIII pen. That means it is expecting to retrieve some new data from the message queue. And the thing is, the task B already posted it, correct? So that means when I call uC-OSIII pen, when task A calls uC-OSIII pen, it will be able to immediately get the data. It doesn't have to wait because task B already sent the data over. Okay, so task A can immediately retrieve the data and it can carry on. Okay, so when it carries on, what does it do? Okay, it just prints out the data that it has received. Okay, and then the whole thing goes back to the loop. Okay, which is to send the updated value. Okay, which is to send the updated value. So from here, everything is going back to a queue. So again, I go back to, so this is the loop. So I go back to OSQ post. Okay, so everything will happen the same way in a loop, because I will come here, I'll post, I will say SEMPEN, and then since semaphore value is 0, I will not be able to get, and then I'll go back to task B. I will take the new updated value, increment again, and then send it back. Okay, so again, when I send it back, I need to wait until the task A has called OSQ_pen, then the task A can carry on. Okay, so you can sort of see the whole sequence, and you have an idea why and how the message queue works, okay, and why we need the semaphore. Okay, again, the semaphore is needed more for the synchronization, because I want to implement the solution such that task A sends the data to task B increments the data and sends it back. Okay, so that is the idea. Okay, so let's go ahead to build the solution and test it out, okay, and see how it works. Okay, so it's running very fast. Let me stop it here. Okay, so if I go back to the very beginning here, so you can see at the very beginning, data sent from task A, that means that is the initial value 0, and the value received in B is 0, and then task B increments the value and sends it back. So the data received again in task A is 1. Okay, so that is one iteration of the entire cycle. And then I repeat. Task A sends the 1, task B retrieves the 1, increments to 2, and sends it back. And I keep doing this. Okay, so this is again a nice example to sort of show you how message queues can be used. Okay, message queues can be used to sort of make sure that the overall or the tasks that need to communicate by sending data across can use this platform. Okay, so that is the whole message queue idea. Okay, so I will just stop here for a while, just for you to sort of absorb, okay, what we just discussed. Think about it, and if you have any questions, you can put it. You can put it in the chat, or you can discuss. All right.
When you call OS post, what exactly happens?
Okay, so when you call OSQ post, okay, as you can see here, what we are doing is we are sending this message to this queue. Okay, so the message that we are sending is basically just the variable count. Okay,
oh, sorry, I meant OS sem, is it sem post? Yeah.
SEMPEN and SEMPOS, is it?
Yeah.
Okay, the semaphore is more for the synchronization. Okay, because when I call SEMPEN and SEMPOS, basically it follows the semaphore rules, which basically says that if the count is bigger than 1, I will take it and decrement. All right. The moment the count is 0, if I try to do a SEMPEN, I'll be blocked. Okay, so the semaphore is used to sort of synchronize, to make sure that after I post, I want to wait until task B has received the data, and then task A is able to continue. Now,
so I'm waiting for the value to become 0.
So I'm waiting for the task B to retrieve, increment, and send back.
No, I mean, when you say OS SEMPEN in task A, right? You're waiting for it to become 0. You're waiting for count to be 0.
No, right? SEMPEN is nothing to do with count. Okay, SEMPEN is to do with its own semaphore value, the MySem value. Okay, the initial MySem value here is
0.
Okay, so initially when you create is 0. So which means that the very first time that I call SEMPEN, there is already no semaphore available. Correct? So the very first time that I call my I call sempen, I mean I want to take a semaphore, there is actually no semaphore because the value is 0. So that is why the very first time that I call it over here, I will straight away get blocked. Okay, because there is no semaphore available, so I get blocked. Okay.
So when task B runs OS post, there is a semapen available,
yes.
and task A resumes.
Yes.
Okay.
So the whole idea of using the semaphore here is more to synchronize this. Okay. So maybe I will show you. Okay. So if let's say I remove this sempen. Okay, if I remove this sempen from the task A, okay, and then I run, you will see the issue. You will see what happens. Okay, so let me run it here. Okay, so you can see that it is always in 0. And task B, there is no printout from task B at all. Okay, again, why? Because this is, again, the concept is you take from the right hand and give to the left hand. Why? Because your task A send or post a message. Okay, your task A post a message, but it straight away try to retrieve a message from the same message queue. Okay, so it never allowed a chance for task B to run.
I think what I don't really understand is why can't I use OS post for both task A and task B? Why do I need to use OS-pen and OS-post?
Because the post is to say you want to put a message from the current task to the queue.
But in task A, I'm also putting a message from task A to task B.
Yeah, task A is putting from A to B, correct?
Yeah.
But after that, I am expecting to retrieve from task B.
So why can't I use OS-post in task A?
OS-post in task A.
Yeah, why can't I just use OS-post for both task A and task B? Or conversely, OS-pen for both task A and task B? Why do I need to use sempen and sempost?
Because if you use sempost here, okay, then you will be allowed to increment the semaphore, correct? Because current semaphore value is 0.
Okay.
So if I use sempost here, current semaphore value is 0. I will increment semaphore, which I'm allowed to do, so I won't be blocked. So if I'm not blocked, then I will be able to immediately come here and do the sempen. I mean the OSQ pen. The whole idea is I want to do something here that makes sure that I go to a block state.
Okay, so when I run OS-pen, the semaphore value becomes 1.
No, when I call sempen, I will try to take the semaphore, which means I'll try to decrement the value.
Oh, but it's 0, I can't decrement it.
Yes.
So then I'm blocked.
Yes.
Then for the other task, I try to decrement the value. I mean, for the other task, I will increment the value.
Yes.
And when I increment the value, what happens?
Then the task that was waiting for it will be able to get it, which is the
Is it only because task A has higher priority? That's why
no. Whichever task it is blocked, the highest priority task that is blocked waiting for the semaphore will get it.
So when I run OS-post, I immediately get blocked. For task B lah. So for task B, when I run OS-post, I increment the value.
Yeah, when you run sempost here, you increment the semaphore value, which means that task A will immediately get unblocked.
And OS-post, when I run it, why is task B blocked? It's because task A has higher priority.
Yeah, so task B doesn't get blocked, it just gets preempted by task A.
Oh, okay. Which means task A has higher priority.
Yes.
Okay. Okay, thanks.
Okay, so yeah, so this idea of course using the semaphore is not ideal, right? Because we are just trying to use semaphore as a means of synchronizing this whole flow. Okay, and this comes about because we are using this general queue, this my queue. Okay, so since it's a general queue, the task that put to it can also straight away retrieve from it. Okay, so this general queue, my queue, of course, is useful. Okay, and it can also be used in a lot of scenarios. Now, the next thing that we're going to look at, okay, is this other idea called the task queue. Okay, so let's come back to our slides here. Okay, so what is task queue? Okay, so let me come back here to the slides. So in a message queue, we create a generic queue and we can post to it and we can retrieve from it. Okay, so that is the general message queue concept that we just saw. Now in Microsoft OS, there is also another thing, okay, which I feel is better, and that is basically called task queue. Okay, task message queue, where instead of creating a new separate queue, we use the queue that is directly linked to the task itself. Okay, so it is like every queue has its own handphone number, right? And then we directly call that number. Okay, so instead of trying to call a general line and see who wants to pick up or something like that, we can directly communicate with the task that we intend to send or retrieve a message from. Okay, so instead of using the generic message functions, we will use these message functions called OS task queue post and OS task queue pen. All right, so the idea is the same. The whole concept of the message queues is the same. Only thing is we are using it directly to the task instead of a generic message queue. Okay, so that is the only difference. Okay, so what we need to do is when we create the task, we need to actually specify a task queue size. Okay, so that is the first thing that we do. Okay, we need to make sure that the task queue size is specified in the OS task create. Okay, now the next thing is, instead of saying OS queue post and putting the message queue, we say OS task queue post and we say which task we are talking about. Okay, so we need to reference the task using this format, which is actually the address of the task control block. Okay, so if I'm currently in task A and I want to send a message to task B, I will say OS task queue post, and the first parameter would be this, will be the address of the task B TCB. So when I do this, okay, that means I am saying that I am sending a message directly to only task B. Nobody else will retrieve this message. Okay, and similarly, okay, so if this, now I'm in task A and I'm saying that I want to send directly to task B. And subsequently, when I want to retrieve a message to my own task queue, I call OS task queue pen. So if I'm in task A, for example, and if I call OS task queue pen, okay, that means I'm looking for people or other tasks to send me a message directly to my message queue. Okay, so I can now clearly distinguish the various queues that are involved. So it's no longer a general queue. It is a specific queue. When I'm sending to somebody, I send to their queue. When I want somebody to send to me, I expect to receive it in my own personal queue. Okay, so that is the only difference. Other than that, the rest of the concepts are the same. Okay, so let's see that, okay, in action and look at the difference. Okay, so if you look at this task message queue example, everything is the same. Okay, the initial stage in the startup task, the key difference is that we need to specify a task queue size. Okay, we need to specify a task queue size to say how many messages we expect. We want to set aside in the buffer to send or receive messages. So for both task A and task B, I specify this. Okay, I specify this task queue size, and subsequently in the task A, now you see I don't need the semaphore anymore. Okay, I don't need the semaphore anymore. Okay, why I don't need the semaphore anymore? Okay, so let's see what is happening. So let me come back here. So the main and startup tasks are all the same. So let's just focus on task A and task B. Okay, so I'm just going to focus on task A and task B. Okay, so what is happening in task A? Okay, what is happening in task A? So task A is going to do a task queue post, but instead of posting any to any general queue, I'm posting specifically to task B. Okay, so I'm going to say that when task A runs, the first thing I'm going to do is I'm going to say task queue post, okay, to B. So I'm saying that I'm going to send a message over to B. But we know that task B is not running at the moment. So this message is being sent over, but task B is not able to retrieve it yet. Okay, it's not able to retrieve it yet because task A is still running. Okay, task A is still running. So task A will post. Okay, but after it posts, I immediately say task queue pen. So when I say task queue pen, I'm referring back to my own task. So if I'm in task A, this task queue pen is referencing task A. That means I'm expecting to receive some data on my own message queue. Okay, I'm expecting to receive some data on my own message queue. So what is happening is over here, I am now saying that task queue pen. So this task queue pen is referencing its own task message queue. So means it is A. That means I'm expecting somebody to send me data. But the thing is nobody has sent anything to task A yet. Correct? So since nobody has sent anything to task A, you will go to a block state. Okay, so the moment it goes to a block state, okay, then I can allow task B to transition. So until then, task B was in the ready state. Okay, and the moment task A goes to a block state, you can go to a run state. So once it goes to a run state, what happens? Let's look at task B. The very first thing that it does is it calls the task queue pen. That means it is expecting to receive some data. Okay, and in our case, we know that we already sent the data earlier. Okay, so when I call task queue pen, okay, that means for my own task B, I will be able to immediately retrieve the data that was sent to me. Okay, so I can straight away just carry on. I won't have to be blocked waiting for anything. Okay, because task A already sent the data. Now I'm just retrieving the data. Okay, and once I retrieve the data, what do? I increment my value. Okay, so I do a plus plus. After I do a plus plus, what do? I send my updated value to task A. So you can see that I'm doing a post specifically to task A. Okay, I'm doing a post specifically to task A. So at this point of time, what is happening is I'm saying that I want to do a task queue post. Okay, to A. Okay, and once it goes, I do a task queue post to A, and since task A was blocked waiting for some message to come in, it will be able to immediately retrieve and unblock. Okay, so that means until here it was blocked, and once this thing happened, it will immediately go to the ready state and since task A is higher priority, it will run. Okay, and once it starts to run, the same thing happens, correct? That means I was originally blocked here, but now the task B already sent the data over to me. I will unblock and I'm able to print out the value received. Okay, so I'm just going to go ahead to do a print. And then the whole sequence just repeats itself. Okay, so you can see that. Okay, so let's look at the demo first.
Sorry, I have another question.
Yeah.
So, at which point does the scheduler pick up that task B is going to be blocked and task A is going to be to resume? If you go back to your previous diagram. So, based on what you're saying, it seems like the scheduler constantly puts task B back to the ready state and checks if task A is still blocked. So when I run ++, does the scheduler check if task A is still blocked?
No. The scheduler will
detect for the task A's mailbox, is it?
Okay, so basically how the OS works is the OS will keep track of the events, okay, that have put a particular task to any state. That means currently task A is blocked, right? So
it's listening for a certain event.
Okay, so when task A is blocked, it knows that it is blocked because of this particular event. That means it is expecting some data to be received. Okay, so only when that is fulfilled, then the state change happens. So any other activity that happens in any other task will not cause task A to switch. But the moment the event that we have been waiting for, that means that someone has put something onto task A's task buffer, then we know that the task A that was blocked waiting for this can now be unblocked. So that one is managed at the back end. So the OS will keep checking to see what event has happened and whether that event is going to cause a change in any of the states from the block to unblock. Okay, so
it's kind of like an event listener.
Yeah. So you will keep on tracking to see whether the event that will unblock the current task has happened.
So if let's say my CPU is very fast and I somehow when I send the message back from task B to task A, and I immediately, my event listener is not fast enough to pick up that the state has changed, can task B run the green box before task A resumes?
I mean that will not happen because the OS is guaranteed to perform a context switch the moment the event happens. Okay, so I mean if you say that your OS does not do a context switch fast enough, then that probably would not classify it as a I mean it is still possible, okay, if your OS is doesn't have any real-time constraints built in, okay, then there's a possibility that it may go back to the loop and try to do something else.
Yeah, but generally that won't happen now.
Yeah, so generally the idea is, since we already have this concept of prioritized preemptive scheduling, the moment a higher priority task becomes ready, it will take over the CPU.
Okay. Okay, thank you.
Yeah, so you can see that this idea of using the task queue is of course a lot more intuitive, all right, and it's a lot more cleaner compared to trying to use the semaphore, because when you use the semaphore, it just adds another layer which we don't really need. All right, whereas here is more direct. That means we know exactly what we're trying to do. We are trying to send data from task A to task B. Task B does the computation and it sends it back. Okay, and task A receives it. Okay, so if I were to run this now, okay, so you can see the behavior as before. Task A send to task B increment and send back, and then the whole cycle just keeps repeating. Okay, so the idea is again to show you the two different approaches. Again, even though task message queue seems a better option, in some cases maybe the generic queue might be more applicable, again depending on what you're trying to do. In our case, it is only one task to another task, so directly using task message queue may be easier. Okay, but if you have a different scenario where you need to put to a message queue while many other tasks may need to read from it, then a generic message queue may be a better option. Okay, so it all depends on what you are actually trying to do. Okay, so this these two demonstration here is again important to understand and get the idea of how it works. Okay, why? Because this is basically the concept behind how you're supposed to do the assignment 2. Okay, so let me bring up the assignment 2 over here. Just give me a minute. Okay, the deadline for assignment 2, I believe, is end of week 12, I think. I have to check the date again. Okay, so you have for about another 3 to 4 weeks. Okay, so in this example, basically what you're supposed to do is supposed to create a calculator. So it's a very simple operation. Okay, the only thing is you need to break it up into 3 separate tasks. Okay, and task input, task operation, and task result. Okay, so what you need to do is you need to capture it in the correct sequence. Okay, that means the inputs must be captured one at a time, interleaved with the operation. Okay, just like how you use your calculator. Okay, if I want to do 2 plus 5, I cannot say 2, 5, and then plus. I must first capture the first number, the operation, and second number. Okay, and then I display the result. Okay, so I need to be able to call the task input twice. Okay, but in the middle of that, I must call the task operation. Okay, and finally, I must call another task to print out the result. Okay, so that is the minimum task that you need. If you think you want to have more tasks, again, that is up to you. Okay, so this is just an example only. So for example, you ask the user what is the first operation. He gives so the first number, he gives a number. Then you say, okay, these are Potter operations. Okay, and then you say, okay, what do you want to do? Okay, I want to do a addition. Okay, then the second number, and then I give the result. Okay, so you cannot use any global variables for holding data. Okay, so you cannot just say, okay, number 1, number 2, result, all 3 global variables, and I just solve it that way. Okay, so you cannot use global variables for data. Only OS constructs are declared as global. So what are OS constructs? Okay, that means things that are related to the OS functionality. Okay, that means things like you create a message queue, you create a semaphore. All these are OS related constructs. So all of these have to be global. Okay, all of these have to be global. But other than that, you cannot declare variables that hold the data for computation to be global. Okay, of course you are free to use any mechanism that you like. Okay, so you only need to worry about integer values. You don't need to worry about floating point. Okay, and the quotient is the answer. Okay, so if you do division, if you have a decimal point, you can just discard it. All right, and you can use printf and scanf s. Okay, so I've given you some example here. Okay, so when you are developing a solution, okay, please remember you also need to update the appconfig.h. Okay, so even though all the general code is inside the main, there is also another header file appconfig.h where you need to specify the priority levels, the stack sizes, and so on. Okay, so inside this file, there's only two things that you need to do. One is the stack size for all the tasks that you create, and the priority levels. Okay, so that is inside appconfig.h. Okay, so again, I think if you understand this example, okay, so I'll upload these two examples. Okay, these two folders, the task queue and message queue example code, I'll upload to Luminous. Okay, so you can have a look. Okay, and you can see for yourself how it is done, and you just can build up from there. Okay, you can just take the similar idea and build up from there and just extend it. Okay, and from there you can easily do the project. Okay, so it's up to you what you want to use, whether you want to use message queue, you want to use task queue. Okay, it's all up to you. Okay, but as long as you follow the sequence and the requirements, then it is fine. Okay, so it is not very difficult. Like I said, I will be passing you the code that I showed you today, both the task queue and message queue, so you can very easily use that as a baseline. Okay, and then build upon from there. Okay, then I think should be manageable. Okay, so the deadline again for assignment 2, I think I set it as the end of week 12. Okay, so we are now in week 9, so we have about another 3.5 weeks. Okay, so as a question for term paper, yeah, we only need to have enough instructions to fulfill that square operation. You don't need to have we are definitely going to have a lot lesser instructions than the MIPS. So you just need to make sure that whatever instructions you wish to implement are enough for you to complete the required operations. Okay, so I think that's all I have for today. If you have any other questions, you can ask me. If not, I will see you all next week. For term paper, yeah, you don't need to handle any exceptional cases. Okay, as long as it's enough to handle the requirements, it is fine. Okay, no other questions. Thank you. I'll see you all next week. Okay, bye.